Hi everyone. So we're going to pick up where we left off back before spring break, during our last class. We had started working on using the integrated rate law to start to solve problems. So what I have up on the slides, what you see right now, are just a 2/3 of summarizing what we covered, right? So there is a handout that I gave you before we left, and it's also up on EC Learn that summarizes our rate law, our integrated rate law, the graph that linearizes the data for first, second, and zeroth order reaction. So I know one of my classes, we started, just started a problem like this together before we actually got together on Friday, and then I gave you a bunch of practice problems. So usually my plan right now is to keep our lecture videos to just theory, but since we're finishing off this chapter, I thought and also to kind of kick the tires a little bit on some of this technology, to do one problem with you right now. But in the future, my plan is to separate theory from practice problems so we can kind of streamline the information that I'm giving you guys. So let's read through it, and then we're going to attack this problem. So it says, we have the reaction, SO2Cl2 goes to SO2 and Cl2. It says the rate constant is equal to this number at a certain temperature, and it's asking what graphical plot will linearize the data, right? So how would we obtain the rate constant? And then what percentage of the initial amount of SO2Cl2 will remain after 2 hours, right? So I'm just going to start to practice using this new stylus and everything. So one thing right off the bat, to answer that first question, what graphical plot of data was used to obtain the rate constant? Well, it's a little bit vague, but what it's asking is if we look at the rate constant, right, we're given an indication of what type or what order of the reaction is overall. Because if we look here, those are the units for the rate constant. And we know for a first order reaction, right, our units for K will be in the units of per second. And that's always the case. And so I know usually my handwriting is a lot better on the board. I'm still getting used to the stylus. At one point, I might actually switch over to cursive because it's actually easier to write in cursive with the stylus on the iPad than actually print. But I'm going to try to keep print unless it entirely fails. So for us, this answers our first question. What graphical plot would linearize the data? Well, if I know it's a first order reaction, a plot for a first order reaction, if we go back one slide, which I won't because I'm in the middle of drawing, if we have the natural log of the concentration of whatever our reactants are plotted against time, we should have a straight line. We can get a slope from that. We know that the slope m is going to be equal to negative k. How do I know that? Because the equation for a first order reaction, the integrated rate law, is going to be the natural log, it should be that, make it a bracket, concentration of whatever A is at time t equals negative kt plus the natural log of whatever the concentration of a reactant A was at time 0. So we've already answered our first question. All we needed to know was the little bit of information over here, which was our the units of our K. So let's try the second part. What percentage of the initial amount of SO2Cl2 will remain after 2 hours? So let's go to the next slide, and it should be blank. Good. And what we'll do is we'll take that problem, and as always, what we're going to do is going to list our givens, finds, and then we'll attack the problem. So our givens are, we said our rate constant K is equal to 2.20 times 10 to the negative fifth per second. The temperature we were given was at 593 Kelvin, though we'll find out this will eventually be unnecessary. When we get to the next section, we're just going to find out that K varies with temperature. So to be explicit, we need to mention what K and associated what temperature. The time that we're given is 2 hours. And that's about all the information we have. Then we're asked to find, right, the concentration, or rather the percentage of SO2 Cl2 remaining, right, after 2 hours. So, what equation might we use? Well, we've already identified it as a first-order reaction. We're talking about changes in concentration, so why don't we start applying, or at least try to apply, our integrated rate law for a first-order reaction, which will look like this. So I asked myself some questions. What am I looking for? Well, effectively, I'm looking for a percentage, so oops, that's not what I wanted. Let's see if I can get rid of, oh, no, that's going to erase everything. Still getting used to this, guys. Let's put that back, right? What I was trying to do was highlight this. There we go. We're trying to find the concentration of A at time t, right? So, what do I know? Well, I know I have K, because I can see that up here. I know I have T, because I see that right here. We don't need to know temperature because that's more there to clarify what K is, because it needs to be a specified temperature. And a percentage is actually going to be a ratio between these two. So what I can do, I don't care what the concentration is. I could say I'm starting with 100% of my A. Well, what percentage, right, of AT will remain after time has elapsed? So actually what we need to know is even though we're not giving a concentration to start with, I know I have 100%. So I can put in ln 100% and we'll just solve for A sub t in the units of percent. So let's try that. So I'm going to erase all this and let's start plugging in. So we know our equation is going to look like this. So we have the natural log of the concentration of whatever A is. In case A for us will be SO2Cl2 because that's our reactant. It's going to be equal to negative KT plus the natural log of how much A I started with. So let's start plugging in our numbers. So I'm still trying to find A sub t. That's the percentage I'm trying to find. And I don't know why my it's the way that the stylus works. My equal sign kind of looks like mountains. I don't know. Yeah, that's really weird why it's doing that. So that's a negative sign times my K, which is the 2.20 times 10 to the negative fifth per second. My time is 2 hours. And maybe you're already seeing a conflict right now, why we can't use this equation just as written. And plus the natural log of 100, which is assume percentage, whatever that is, right? What we notice right away is take a look at our units. That's per second, does not cancel with hours. So what we're going to need to do, let me see if I can do this. Nope, again, can't just delete one line. So it's per second and then hour. And it's a number 2. So what we'll need to do is take the 2.00 hours and then convert that into seconds. So in 1 hour, there's 60 minutes or 3,600 seconds. If I do that math out, I end up with 7,200 seconds. Now, there's my per second, and seconds will cancel. So I plug that in. There's my natural log of the concentration of A at some time. Sorry about that. It equals negative 2.20 times 10 to the negative fifth per second times 7,200 seconds plus the natural log of 100, which is just a number. So we plug everything in. I'm going to erase everything that's on the screen, so pause if you need to catch up, but I'm going to restart here. So we had our natural log of the concentration of A, again reminding ourselves it's SO2Cl2 at some time t, which is 2 hours. Doing out our math, we should get negative 0.729. Oh, actually, I think I might have made a mistake. Give me 2 seconds. So negative 2.2 times 10 raised to the negative fifth times 7200 plus the natural log of 100. Ah, I did make a mistake. My bad. I thought that was it seemed a little too small. This side should be 4.44677. I'm keeping a bunch of sig fig just because when we're dealing with exponentials, if you round early, you can compound that problem of rounding error. So we have that. What we can do now is exponentiate both sides. So if I exponentiate, which means e raised to the natural log of concentration of t, e raised to that, well, these two are going to cancel out. It basically brings down a concentration at time t. Well, e raised to the 4.44467 equals 85.35. And remember, my units were percent, so I don't even have to worry about the actual amount that I started with. So there we go. After 2 hours, the amount of SO2Cl2 that remains is 85.35%. So not too hard. The hardest part is usually doing the exponentiation part that people kind of forget about or get confused with. So let's move on. So, oops, it looks like there was a little bit of a conversion error, but that top part up here, we just get this stuff right here, that's supposed to be our heading. So now we're looking at reaction rates and temperature. So everything we've looked at so far has all been one temperature, right? Just like in that last problem, was specified exactly what temperature. Well, what happens if the temperature changes, right? So we've looked at this reaction the entire time, or not the entire time, but it was our example reaction we've been using for this chapter. However, everything was at one temperature for us, and we've already alluded to this, but rate constant is going to depend on temperature. So just to give you a visual example, here we take a look at magnesium metal. It will react with water. It's higher on the activity series, so it's going to reduce water. But if it's cold, we're going to see it actually happens very, very slowly, or if at anything, it might not even happen at all. So it looks inert. But if you heat that water up, all of a sudden, that magnesium starts to react with the water, producing magnesium 2+ hydroxide, and you can even see the bubbles forming H2 gas. My guess why it's pink is they've probably added some sort of indicator dye that's probably telling you that it's becoming basic. So though you won't be doing it yourself in lab, you'll see that we use things called indicator dyes that will tell you if a pH is basic or acidic. In this case, it's basic, but we're not going to even touch on that till we get to chapter 17, so don't worry if you're a little confused on that. All we're looking at right now, take-home message, magnesium appears to be very, very either not reacting or very slowly reacting with the cold water, but when I increase the temperature, the reaction increases to the point where we actually see it. So why is this happening? So the way chemists describe this is through kinetic molecular theory, or which we introduced technically when we were talking about the ideal gas law in 1101. But here we're going to up it a little bit more. Instead of just talking about the gas behaving as small little particles, well, what happens when those particles collide and a reaction happens? And that is going to be dictated by collision theory. So let's read through it, and then let's apply the definition that's on the screen to the graph that's below. So it says collision theory. As the average kinetic energy increases, right? So if we increase the temperature, the average kinetic energy is going to increase. The average molecular speeds increases, and thus the collision rate increases. And this is exactly what we were talking about when we were discussing vapor pressure, right? We know that when we have at low temperature, we have this peak here where the majority of finding a particle with a particular kinetic energy is going to be found here. So we see that it has low energy. And then when we increase the temperature, it's the same area under the curve, but it's a different distribution. And so if you've been paying attention to the news, the idea of flattening the curve that you've been seeing about the coronavirus, even though Dr. Fauci has come out and said, yeah, the same amount of cases will actually be different, but it's a similar idea of flattening the curve. instead of having things happen very quickly, in terms of the virus, we're talking about slow-moving particles. Most things are down here, but if we flatten the curve, we push more of the particles to higher energy in this case. So what we see ultimately is over here, right? There's some barrier that, just like when we were talking about PVAP, that the particles need to have, instead of just evaporating. If particles have this amount of energy or greater, that means a reaction will occur, or reaction can occur. Not always, and we'll talk about that in a second. So a reaction can occur if it has energy over this certain amount. So there's our minimum energy needed for reaction. We use the symbol EA, and we call that activation energy. So activation energy. So as you can kind of see, it's going to be easier for me to write in cursive. So that top part by activation energy is in cursive. The bottom I'm trying to print, it's not working. I'm going to probably transfer over to writing in cursive in the future. So if you have trouble reading my handwriting, please let me know as soon as possible so I can try. I've already ordered a better stylus. I'm using an okay stylus right now and trying my best with that. All right, so let's keep moving forward. So we have this idea of activation energy. It's the minimum amount of energy needed for a chemical reaction to happen. So what happens when those particles collide, right? So we look here and we start with our reactants. That's how we always start. So we have an A and we have a BC. A is going to slam into this molecule here. And if A slams into BC and a reaction is possible, what you see up here is the bond between A and B is starting to form, while the bond to B and C is starting to break. And so we call this the transition state. So a transition state, it cannot be captured in a lab. I'll say isolated, how about that? Cannot be isolated in a lab. Why? Because it's basically on a knife's edge. Bonds are half forming, half broken, right? So what's going to end up happening is it's not a stable state. It exists. We've been able to see it when we slow things down, but you can't trap it, is the idea. But our transition state, despite being unstable, is actually going to be able to lead to roll downhill to form our products. So let's take a look. I'm going to erase this. Right? So we need to have a minimum amount of energy, which we see here, that is going to be needed by the by the reactants in order to form this transition state. So we can start to see where temperature is starting to come into play here. If my reactants are moving too slowly, they might start up this hill but never reach the top if their kinetic energy is too low. Well, they'll just fall back down and nothing happens. However, if my reactants have enough energy when they collide, so a higher temperature or higher average kinetic energy, they can get over this barrier and then flow down, energetically speaking, to form the products. And so what we see here in the products is now AB have formed a covalent bond, and then C has now basically moved off by itself. So we've broken a bond between B and C and formed a new bond between A and B. So how are we going to quantify this? So we can see on an energy diagram that, yeah, having enough energy is going to be necessary to get over the activation energy so the reaction can go forward. And we know that kinetic energy and energy in general is related to temperature. So how do we take this microscopic idea? Let me go back for a second. This microscopic idea of looking at individual molecules reacting and then apply it to a larger sample. And to do that, what we're going to do is use the Arrhenius equation. So the Arrhenius equation is written below. And this was discovered by both Arrhenius and Van 't Hoff. So one name you've heard before, Van 't Hoff, and Arrhenius is a new name. So the Arrhenius equation is going to relate the rate constant K to all of these other variables. A, E, A, R, and T. So when we go through, we have some that we've already seen before. Activation energy, we just saw that on the last slide, right? We said that's the minimum amount of energy needed for a reaction to take place. If the molecules don't have that energy, the reaction actually does not go forward at all. The gas constant, we've seen this one pop up before, right? We're dealing with energy, so we're going to be using the value of 8.314 joules per mole per Kelvin. Sorry, it's a little, again, I'm doing my best with the stylus I got, right? So that's the K, the R we'll use. It will work with other R's, but you're going to be really careful with your units, so I'd recommend sticking with this. Temperature, we're all familiar with by now. Another thing that we need to pay attention to, though, is right here is our Kelvin. Again, just like with using the ideal gas law, we're going to need to have an absolute scale. The last thing that we can look at that we have never discussed before, it looks like it got cut off a little bit, is the collisional frequency factor. So, what is a collisional frequency factor? What this is describing, it's just a number, you can't predict it, it needs to be measured experimentally, but it's saying that orientation matters. So if I have a molecule AB and it's reacting with C, if AB are going to form, BC are going to be forming a bond, C better be colliding with B. Because if the molecule comes in reverse, maybe C, if it bumps into A, can't react with A. So it needs to be directional. If C is making a bond with B, just like I'm showing here, C better hit the atom B. However, like I'm saying here, if C hits A, we're saying, well, that's in the wrong orientation. A reaction won't happen. What the collisional frequency factor is basically a ratio telling me how often does a successful reaction happen. Right? And again, if we think about other orientations, if A and B were on its side and then collided with B, or collided with C, maybe another reaction doesn't happen. It's just telling you how often will a reaction occur that results in a successful reaction. That's what A is. So how do we use the Arrhenius equation? Well, we have two different ways we can do it. One, the one that I like, because it's just, an easy way to remember, and I found it easier to use, was the one I had on the last slide, which said, I'm in the wrong stylus, there we go, that K equals that collisional frequency factor, Euler's number E, right, raised to, we said the negative EA over RT, just like in the last slide. Doing some, using our log rules, what you can do is take this equation, apply the natural log to both sides, which we're seeing here, and what you'll do is you will simplify the equation. Well, not simplify, but you're bringing down the variables that were once in the exponents, so these guys here, and bringing them down into like one level of the equation with no exponents. We also see, this is still the Arrhenius equation, we've linearized the data. So there's our linear data, or rather a linearized equation, so our linear equation, with our y being equal to the natural log of k. So even without seeing any slide or any graph yet, we already know y is going to be ln of k. My x I'm seeing here, I can do 1 over absolute temperature. My slope m, I can see, is going to be negative EA over R. So there's my negative slope. I don't know why it gave me a lasso tool. I'm trying to draw a straight line. There we go. So my slope equals negative EA over R. And then the last bit is going to be the collisional frequency factor is actually going to be here. So the ln of the collisional frequency factor. So one thing we need to pay attention to, let me erase that and make it a little bit more clear. ln A, the collisional frequency factor being the y-intercept, it does not mean the natural log of A sub t like we've been using before, right? A here in the Arrhenius equation is the collisional frequency factor. A here in our integrated rate law for the first order reaction just means any generic reaction. So just make sure you're keeping track of your variables, that you know how to use them. So exactly what we just predicted, this is what we already derived. There's my y-axis, ln of k. There's my x-axis, 1 over t. Here's my slope. My slope is 1 over negative EA over R. And then the last bit we have is our, oops, sorry, it should be here when it hits the y-intercept. And there is the natural log of my collisional frequency factor. So the last thing we're going to talk about is catalysis, and then we'll be done with the lecture. So sorry, I'm still working on timing. I know it's a little bit long, but we did do a couple practice problems. We're skipping reaction mechanisms for this. They tend to be more complicated. It's going to be difficult to do via online lecture. So we have elected to bypass the reaction mechanism section of this chapter. So we're going to stop with catalysis. So the last thing I want to talk about is catalysis, right? So let's read the definition and explain what's happening. So it's a substance that increases the rate of reaction without itself being consumed in the reaction. A catalyst is used in one step and regenerated at a later step. So everything we've talked about thus far has always looked like a single step reaction. If we were going to show hydrogen peroxide degrading into water and oxygen gas, we've typically seen it written as one line, right? So one reaction. However, in real life, what is actually happening is that it is a stepwise process. Or sorry, let me correct myself. If hydrogen peroxide is allowed to just sit on its own, this reaction does happen by itself in a single step. It's just very slow. If you add the presence of a catalyst, in this case, I1-, a catalyst can accelerate how fast the reaction happens. So instead of happening in one slow step, what ends up happening is the reaction is then divided into two steps that happen to be faster than this single step alone. The way those steps were made faster was by the presence of the catalyst. What makes the I- a catalyst and not a reactant? The fact that it is used as a reactant in one step and then regenerated as a product in the last. If we treat this like a spectator ion, like we were doing our net ionic equations, you cancel out things that appear on both sides of the reaction. And if I added up both sides, well, we'd see that actually it falls out as well. And then we're giving our overall reaction. So that's why it's a catalyst, right? It appears both on the reactant and it regenerated on the product side. Oh, I guess I didn't have a slide specifically for that. There's one other term that I want to bring up. So we have our idea of a catalyst, right? We said I- is a catalyst because it was a reactant and then regenerated again as a product. One new term that we need to also learn is something called the reactive intermediate. In this case, it is generated as a product and then consumed in a later step as a reactant. So let's put that down. Reactive intermediate. Reactive intermediate, right? Sorry, I'm still learning how to use this. So reactive intermediate is going to be generated as a product and immediately consumed. So you see it's generated as a product and immediately consumed. So that's going to be our reactive intermediate. So what does this look like on an energy diagram? So like any other energy diagram we're looking at, so it says potential energy is on our y-axis. We can just think of that as energy, right? Or if you want to think directly as potential energy, it's like going up a hill. It takes energy to go up a hill. As you go higher and further away from the center of the Earth, your potential energy increases. So what we see here is we have our H2O2, so that's our hydrogen peroxide that will break down into water and oxygen gas. So I'm actually going to start on the right side. So over here, the uncatalyzed reaction, we see there's a single step with its activation energy. The reactants have to have enough energy to get up and over this curve, and then when it falls back down to a lower energy, our products are created. When we add the presence of a catalyst, in this case, right, that was our I minus, we see there's actually two steps, and because of two steps, there's actually two activation energies. It's a little hard to see, but actually this little bump right here, what I just drew, we can call that EA2, where this one might be EA1. So we see the first activation energy, it's still pretty large, but not necessarily as large as the uncatalyzed step. So there's our step 1, and then, oops, let me just make that a little bit more clear. Step 1 and step 2. And so the two steps combined is actually quicker than the one step over here. One thing that I do want to stress is the high school definition of a catalyst, and some books still use this definition, is to say that catalysts reduce the activation energy. Catalysts do not reduce activation energy. And I'm going to be very specific about what I mean. It is not like it takes this uncatalyzed reaction and then drops the barrier to somewhere lower, right? What they do is they take reaction through another path. So take reaction through another lower energy, let's say lower E path. Right? What does that mean? Well, it's like the idea of summiting a mountain versus going around it, right? So if you ever climb Mount Washington, you can go all the way to the summit, but there's also a path where you can go up the mountain instead of going up and over, right? Instead of taking one path, you can take Lion's Head. Lion's Head path goes around the summit and then down the other side of the mountain without ever summiting. If you had your exact identical twin and then one person went over the top of Mount Washington versus taking Lion's, what is it called? I forget now, the Lion's Path, Lion's, whatever it was, you can cut off a significant amount of your trek. You both started and end in the same spot, just like a reaction does, but you took a different pathway. One was lower energy, Lion's Head, that's what it is. When you take the Lion's Head path versus summiting. It's the same exact thing when we talk about chemistry. So this is exactly what we see. The last thing we want to talk about is something, what makes reactions slow versus fast, right? And that's going to be determined by the rate determining step. It is literally whatever the slowest step is. It is the step that determines the rate. That's all we need to know. I will have to tell you if something is slow versus fast, right? So there's no way to look at it and predict it. Maybe there's certain reactions you can, but not something like this. So for us, just know what the definition of a rate determining step is. It literally determines the rate. It just so happens that this is a two-step process, and the first step is the rate limiting step. It means the second step must be faster than the first. If it was slower, then that would be the rate determining step. I don't know why that went so slow. But the last thing that we want to see too, again, when we look at the overall balanced chemical reaction, here we see that the catalyst doesn't appear, but actually in the rate law, the catalyst does appear. So that's another thing to keep in mind, but that shouldn't be something new. We've talked about that before, that the rate law does not necessarily always agree with how the balanced chemical reaction is written. Agree with the coefficients is what I mean. All right, so that's the end of our slide, and that ends chapter 14. If it feels a little bit clunky, I'm going to work on making this more streamlined. Like I said, I've already ordered a better stylus. I'm just waiting for that to come into the mail. So hopefully that was a good start, and hopefully everything will become more streamlined and a little bit better. So I will see you guys all tomorrow at either 10 or 11 in the morning. All right, stay safe, guys.